gonna do today, we're gonna connect what we created in last tutorial with the more robotic framework, so you can understand pretty much how it is something to create completely from scratch to the fabrication, how everything is connected. That's what we call integrated design, right? And we gonna now we were working with a bounding box, and we're gonna project what we created, the pattern, to the real plank of wood, right? You have it here. So that's how it looks. This is the plank that I got from Valentine, something we actually have in the lab. So I think it's nice to, to use like a real example. Okay, so now let's go to the real deal. And we have these curves, right? How do we actually create planes for robots? So the robot can actually follow, right, these curves and mill it. Yeah, so for that we need to create first points, then we will create planes, right? And what is very important is the order, because we want the robot to go in a certain direction, right? Like this or like this. We don't want robot to mill first this, then that, then this, then that. It will cause us a lot of, additional time, and so that's something we don't want to do. We want it to be, optimized and yeah, the way it's supposed to be, let's say. So, all right. Let's create the logic for the linear framework, right? So this one. For the fields, we will create it later. So let's say, okay. Anyway, let's start. We have our curves here, and yeah, what we need to do, this is, maybe it's a bit difficult, but it's really important to understand what I'm doing now, because this is data management, and this is something you're gonna do whatever project you're doing. If it's, let's say, more or less, yeah, if it's not extremely simple, you're gonna definitely run into that. So yeah, this is important stuff. So try to understand it. Okay, so we need to understand this tree that we have, and yeah, it's pretty much divided into branches, right? And each branch has the curves. So yeah, and this division comes from the rows. So for example, now we have, okay, let's bring tree statistics where you can see information about it. So we have 0 to 5 paths, right? 5 branches. If I actually change, where was the change to here, right? If I change it to long side, so it's in this way. Let's see how much we have, right? We have 83. So it's connected with the rows of how it's, yeah, how it works out. I think for us, it's a little bit more clear if it's, for now, this one, long side. Anyway, so what we need to do, we need to, yeah, dispatch paths. The pattern of dispatch is usually true false. So we put them paths, and now we have, yeah, those paths in different boxes, right? So 0, 1, because you understand, right? We want robot to go like this. That's why we divide it like true false. Okay, then we get those branches with 3 branch, and well, just in case, you can simplify it here. So we have the path here, and let's say here. Okay, we'll sort first the lines. Let's output, let's have curves first, let's say. First list, we will reverse the order of those guys and merge it. So we have it this way. I mean, yeah, then we flatten 3. I use the component so you understand, but you obviously can just do it here, right? This is the same. And yeah, these are our output curves. That was easy, but that's not precisely what we need. same out curves. Now we need, the points for linear curves. Why it's like we will create points for linear curves and for curves, curvy curves. Why it's important? Because in a linear, you can just say, just give the plane to robot here and then here, and it's gonna just mill it. But in curves, you need much more planes because you want the robot to follow it. So that's why it's different. All right. For that, let's obtain for the linear, we just need endpoints pretty much. That's our main need here. And same with with those guys. And if we, let's try to merge it. Or no, we need to weave it first. So we have this, right? Okay. Hey, let's weave it. So weaving just, connects in a certain pattern. This one is the simplest, 0, 1. So that's what we do. And we merge it. We flatten the output. Well, okay, let's be consistent. So use flatten tree. And those are our points, out points. Check it out. What is the great way, and I use it all the time, is you see how many points you have here, right? And then you just create list item, and pretty much, just create a slider. Say, see how it goes, right? So it starts from here, great, and all right, cool. That is great. That, you see, and then this goes exactly where we want it to go. That's why we did all this dispatching, weaving, and so on. So now it goes just perfect. Great. Okay, nice. We're happy. Out points, lines. Now let's do the same for curves. Let's switch it to curves so we have like a better understanding. It's here, linear curve. Okay. Okay, so because I don't want, there are different lengths of these curves, and I kind of don't want to, divide it all in the same way. So what I'm gonna do is that I'm gonna optimize the number of points that they have. And for that, we'll obtain the length. The length of the curve. So one here. Let's start from this block. Divide it, I don't know, let's say in 4. And that's our integer, because we want it to be integer. Same we do for this guy, right? So let's group it, optimizing the number of points. This we can just push it somewhere. Okay, and so we just divide the curve pretty much, and we have the curve, from here again. Let's actually create some, that's what works. Some kind of box for it. Otherwise, let's call it curve A, curve B, right? Otherwise, it just starts to get really messy. Okay. So that's what we brought here. Here we hide the curves, and let's also hide like the display. Okay, cool. So let's connect it here, and the number of points we get from here. Right. Same goes with another block. They are all same, and yeah, we pretty much just merge it. We flatten the tree, and this will be our out points curves, right? Cool. So to check it out, let's do the same trick. See how it goes. Okay. Well, that's a bit too fast. I didn't understand it fully. But I mean, you clearly see that it goes in a way that we want it to, right? So yeah, good, great. No, not great. We have a problem. Okay. So there is some problem with one set of curves. And to check that, we can check the curves first, actually. If this is a problem, we just have it from before. Or not. Okay. So that usually the problem is somewhere when it goes from one row to another one. Okay. There is no problem in curves, so it probably is somewhere with the endpoints. Okay, I'm actually gonna leave it here. So, all right. I see. Okay. So yeah, it's pretty much that's what we did here, right? We weaved the points. And that's what we need to do now. And let me think how to do that better. So we need to divide the points. We divided it, and we have all this data structure. And pretty much, I want these points to be going from 5 to 1. Okay, we can try to reverse the list. I think it will do the trick. Right, so now it's gonna be opposite side. I think that's what we need. Okay. All right, let's check. This is the point where I saw the problem. Okay, great. We don't have it anymore, right? So now it goes smooth. Cool. Nice. Okay, let's group these guys. So okay, I'm gonna leave it here to maybe if I want to debug it in the future or something. Right, and yeah, let's bring all of them together. And yeah, group it as creating points optimized for robot milling. line framework. I call it line framework, and another one I called field framework, right? Two different methods that we tried. Okay, cool. Now let's actually bring like a simplified framework for robot simulation. I hope that you have the robot plugin, so because that's what we're gonna use, and you put the library of robots in the folder that I specified. So it's in document like C disk documents, and this is an intentional like decision not to use the robot that we have in the lab, because I want you to completely, you know, understand like the very basic of how it works. And for that, we're just gonna use some random robot. So eventually, hopefully you will, you know, connect better with the file that we have in the lab and the robot that we have in the lab and the setup. So, all right. Let's first bring our piece of wood to the abstract table, right? Abstract table, I call it abstract because it's literally just a box that imitates the table. Yeah, let's do that in the beginning. Let's go here and create a block that will put our box here, right? I mean, you can just take it also, ungroup it and take it here, because that's where we're gonna need it. Okay. You remember that we created a block when we were doing the fields, lowest or highest surface. So bring it here, we're gonna need it again. And this is how the box looks like, right? I mean, if you do the actual work, I mean, if you actually gonna mill it, you would like the table to be much more precise than that. You know, everything has to be quite precise. So, but that's not the point of the tutorial, right? That's why it's just a box. And we need to obtain the surface, the highest surface where we want to put it. And we want to obtain, like the surface. Actually, let's make some kind of box for it. Or box of box. Yeah, not bonding. Okay, so we connected here and we need to obtain the lowest surface in this guy, right? Because we want the lowest surface to be on the highest surface of the table, right? Yeah, that's very clear, just general logic. Yeah, to do that, we just move it, creating the vector between 2 points. And 2 points are central points of these surfaces. So this one and this one, right? And yeah, just do it and move it, right? Yay. Okay, great. We have it here. Actually, let's do this trick. We group it, moving the wood plank to the table, right? And connect this guy here. So now all this pattern is created already in a new place, which is good for us. Okay. Then we actually gonna create the simplified framework for robotic simulation, right? For that, we go here again in the end, and actually I'm gonna preview everything off except the preview and the table, so otherwise it gets a little bit too much. Okay. Great. All right. So what we need to do is we need to open the robots plugin here, right? And bring the components that we need. So the main component is create a program, right? So it's this one. This is what actually creates the code for the robot itself, right? So we'll start from it and feed the parts that are missing. So name, we name it, I don't know, robot program. Right? So then we need to understand or like feed it the robot system. Robot system is pretty much the robot that we use. And here we're gonna use an abstract robot from the libraries that I told you to install. So, well, we're gonna use this one. It's from EA. And we're gonna feed it here. So you already see it emerging in our Grasshopper file, and we see it right as well. And the last important thing that we need to feed it is the target, right? Like what we want the robot to do actually. Tool input. Sorry, okay, I missed that one. Because we want, also to put the end effector that I gave you in the file already, so don't worry about that. Okay, cool. So our planes will be XY plane. We're just gonna put it here for now, but we're gonna also feed the points that we created, either these ones or these ones. But for now, let's create first the tool. The tool is the end effector, right? Something that actually is gonna create the job, either milling or painting or, well, whatever you wanted to do. The list is infinite. So let's name it. The tool that I gave you is called, well, it's called different way, but I called it 7mm bit mill, because that's what it represents pretty much. And we bring from the beginning the mesh tool and the plane, right? So, and I'm gonna explain you what's what. So mesh tool, this is very clear. It's just an end effector. Usually if you create your own end effector, you model it very precisely. If it's an end effector that you bought from somewhere, they give you the model. So that's something you either create yourself or you have it. And then what is important for robot is the plane. Let me preview of it. So it's the plane here, that usually here, right? It really depends on the tool. Let's just be clear. But something that actually does the job. So you're gonna calculate all of these target planes according to the plane in the what's called TCP, right? So yeah, and that's what we need to feed. And we're gonna flip this plane. Well, you need to see it pretty much, but I think here it's opposite direction, right? Flip plane, it just literally does what it shows. It flips the Z coordinate. So we put it in TCP, we put the mesh tool in the mesh, and we connect it to the create target, right? To the tool or end effector. Cool. So the target we connect here, target 1. And it gets red because probably the plane is here, right? And the robot is also here, so that's not the right way to go, but we know that. Yeah, and okay, let's just connect our planes, I would say. Okay, what do we have here? We have the curve one. Okay, nice. Let's move it a bit and connect the XY to the curves. Okay, now it's orange, which is fine, because it's difficult to make it happy, but it just shouldn't be red. Cool. Let's visualize, I'd say, the robot movement so we can understand what's actually going on. For that, we will just do what I do. No, sorry. Deconstruct it first. Deconstruct program targets. Great. And that's where we can see the planes. And we take the first one. And here we just flatten it. And we create program simulation. Right, so connect the program to program. And the time, what we usually do is that it's just, we create a slider that is like that. Very, yeah, it should be from 0, 1, but with a lot of, yeah, numbers after point. So, okay, we see something here, right, already. Cool, and what we're gonna do is that we're just gonna split the list depending on the time in the, yeah, of the simulation. So we can see what the robot, where the robot actually went, you know, and we don't see, let's say, where it will go in the future. So for that, we split the list. And this is the list, and the index is here. It's the target index, right? And we just connect it with like by Polyline. It's gonna be probably orange anyway. And let's create just nice custom previews for us. I don't know, some nice color that you like, or you don't like, doesn't matter. And I'll put system meshes is the robot. So if I preview of everything and just see this thing. Okay, what's wrong with you? Okay. Okay, something is off. Let's see what's wrong. This is our piece of wood. I mean, kind of looks fine though. Why? Okay, this is null. This is not what you want. Ah, because this should be -1. Okay, that's my bad. Okay, yeah, we got a wrong thing, that's why. Okay, cool. Okay, now, well, where to see closer? Now we see how the robot goes. And we see the problem is that the like in between, like the robot stays there. So pretty much it's gonna mill everything in between here as well, right? And that's not what we want. By the way, any questions? Sorry, I forgot.
Not really. It's actually easier than I thought it would be, like to program the robot.
Just to be very clear, this is simplified framework. So, for example, usually you also give the starting position, which we don't do now, right? Or there is a lot of small details, but this is the just essential blocks, right? Of like what it is. So it's not like, you know, this is, I mean, yeah, it is a program, but it's, I mean, you will need a little bit of adjustments before actually doing that. Right? But to be honest, also, yeah, I think that the file that we have in the robot is a little bit overcomplicated. So that's why, like, we decided to, you know, just give the main components so you understand at least, you know, what is the, yeah, what is the main stuff here. But I mean, so I think it's more a bit more complex than that, but it's also not that complicated as many people think as well, right? So here you see what it actually does. right?
Yeah, exactly.
And I mean, essentially, it's a robot. You tell the robot what to do, you know, it kind of follows. It's it's quite straightforward in my opinion. So, all right, group this part, which will be called our robot visualization. Yeah, so that's that. And maybe, well, okay. So as I said, there is a clear problem here, right? What we see is that why it doesn't show again? Because it's 0. Okay, because we want the robot to kind of have, you know, like these points in between in the air. So we want it to go here, then we want it to, you know, go up, and then move in the, like, yeah, move somewhere here and go down. So, for example, right? So we want him to go here up, then, you know, come down, back, mill the curve, go up again, mill the curve. So, right? So this point, this is not what we want. Sorry, not points, but here is polyline, but essentially it's the movement of robot, right? Here you see it clearly. We don't want it to be here. Well, also right now, technically, since it's all, you know, a bit simplified for you to understand the main components, right now it doesn't mill because it just literally is on the surface. So probably, you know, if you mill it, you want it to be a bit lower, but I think it's clear. That's why we're not doing it here as well. So anyway, just a quick remark. Okay, so what we need to do is we need to pretty much add these points, right, for a robot to go up and not to mill what we want to leave. So for that, we need to join these curves and add first these endpoints, right, where we want the robot to leave actually. So let's do it here. Let's join them. Simplify just to keep it organized. And yeah, and actually let's just copy this thing here, right? Oh, because it's just the same. Right, so we copy it and put it here. Only we connect this guy here, this guy's here. Height point and points. And yeah, so let's check it as well to understand what's going on. From 0 here, let's, okay, maybe we need to, okay, I will preview of the robot for now because so now we are, you know, trying to understand which are the points where the robot should go up and down and come back, right? Okay, so this is the main part. And it's not right. Let's come back. Okay, so I mean, unless I'm going crazy, no, it's not. But I think it's not how it should be. Actually, we don't care about it. Okay, I know what we're gonna do. We're gonna find similar member. So remember this component because it's very handy. This is the data we search for, and we're gonna find it in the set that is here, right? What we feed to the robot. Why we do it in this way? Because we want exactly the same structure of it, right? Because now the structure is different, the data structure. And the find similar member, it gives you the index. So, all right. let's just sort it and dispatch it. Let's actually copy it here, not to create mess, right? So we join it here. And yeah, we want pretty much this, like using these indexes, we want these curves. So to do that, we connect it to the list that we are interested in, and indexes we obtained through find similar member, right? Okay, nice. And yeah, pretty much now let's insert one set of points to the list, right? Let's see. So these points we're gonna move in the air. So we need move component, unit Z, right, up, and factor will be, let's say 60. You can also change it. So the motion is here, the items are those. So now if we go to perspective, we see, well, these are the items, right? So it's like the beginnings, and those are the points in the air. Okay, I think it's very clear. So the tricky part is to actually properly insert them, right? So this is the list we are adding to, and these are the items, right? Items, yeah, items to insert, and indices are these ones, right? That's what we dispatched and obtained from here. Okay, cool. So, I mean, let's check it. I mean, I can actually also show you something other way to check it. I think it's in preview. Okay, we can just write it. Points list. Point list. No, maybe it's a bit annoying. Okay. I mean, okay, well, I hope you learned it, but we're not gonna use it. It's a bit too complicated. We just gonna see it with color. Okay, cool. I think that's what we want. We start from the air, we go to the, yeah, well, all methods have their downsides. Okay. Okay. But then we go directly to this point, and I want the end point also to be in the air, right? But other than that, I think it works pretty well. Okay, so, I mean, to do the endpoints, we do exactly the same procedure, pretty much. We find a similar member in the new list, right? And new list is this one that interests us. And the data to search is those guys. Okay, we found their indexes. We sort them as well. So the indexes go from 0 to, right? Yeah, well, from the smallest to the largest. Okay, so then we take list item. We take it from this list and the indices that we obtained, right? And we move. Okay, so then we take list item. We take it from this list and the indices that we obtained, right? And we move them, same as those ones. And we use, yeah, actually exactly the same Z coordinate, right? So now we have them here. And yeah, we need to insert items as well, same as we did before. Insert items. The list to insert is this list. The items to insert are those, right? Those in the air, the end ones. And the indices is these ones. Yes. Great. So Let's check it. Let's check if we have what we want. Okay. Right. So you see, it's not, I want it to go after the last point, but it put it just before that. So that's easy to change. We're just gonna put, yeah, pretty much x+1 in the indices. x+1. So now, okay, just gonna make it smaller because it's very difficult. Is 0. Yeah. Okay, I think that's what we want. Yeah, cool. Great. All right. So this is our, well, let's call this part. Let's group this one and call it obtain endpoints. Okay. And this one, let's call create, I don't know, buffer zones. Right, so this is the list that we connect with the XY planes. I mean, by the way, we also tried with Valentine to use different planes when we did the meeting, but in this tutorial, it's only XY. So now let's see how it all looks. Right. Great. Looks great. Very nice. Now I want us to do the same procedure, but for the fields, because I assume that will be different, right? Because when we have a grid, we have like these movements, and it makes a lot of sense. But when we have the fields, yeah, maybe it doesn't anymore, right? I mean, yeah, there is definitely no grid. So, yeah, I want us to create together another logic. So let's just sort the points from left to right, right? So the robot kind of, does this part first and then goes further. And yeah, because I mean, all of these kind of logics that worked before are not valid for this option. And actually, I want you to always, be critical about what you're doing, right? So yeah, let's do that. And for these, we need well, actually, let's create a switch, a gate. So let's say if we have fields, it will go right automatically to another yeah, another logic. So for that, I'll also move it a little bit further. Let's create a gate here. Stream gate, right? And the stream is this. And the gate is our switch, this one. And let's also make the wire display hidden. Okay, so right now, right, it goes to 0. If the switch is on, it goes here. So I connected this one, and yeah, we'll need these curves to create our different logic of sorting. And okay, so say let's start to just sort the curves from left to right. Yeah, we flatten them. And we obtain endpoints, right? We entwine them. Entwine. This is different from merging, because it always keeps it in these boxes, right? Or it creates boxes, as in this case. We simplify it. And then we flip matrix. So now we have like this data. We have two boxes, right? One beginning of the curve and the end of the curve. And they all are, all beginnings are in 0 and all ends are in 1. And I want to have a box for each curve, right? So I want 0 here and 0 here to be in one box because it will be one curve. So to do that, we use flip matrix, which does exactly that, right? Creates a lot of boxes for each curve. And this will be our starting point and 1 will be our end point. Okay, then we deconstruct the point. We sort it depending, well, right now we use X because I want it to go from kind of left to right, X coordinate of the points, right? And these are the keys. These are the actual, like what I want to sort. And then since it goes, okay. Now I need to reverse it. All right, let's take the item 0 from here. And now we can flatten it. Then we deconstruct point again and sort it again. So now we sort the curves depending on the points. So okay, just to be very clear, so we obtain both points of each curve, right? So for example, we obtained this one and this one, and now we sort them to understand which point is from one curve is closer to the left, right? And yeah. So if you see the coordinates, now we actually opposite. We need this one. All right. Anyway, and then we kind of sort the curves based on these points. So that's the logic. Okay. So we have out curves. Or let's put it in curve actually. Curves fields. Yeah, and let's check if correct or it looks fine for us, right? 0. Cool. Okay. I'm gonna preview off everything except our previews. We'll connect the preview to this curve. So it works. Doesn't matter where the switch went. Okay. So now it's kind of gonna go like this, which is fine, in my opinion. Yeah, I think that's okay. Okay, cool. I think it's fine for us right now. Okay, we group it. Sorting curves fields. And yeah, now we need these curves again. to actually obtain the points, right? We don't flatten it. Hidden wire display. And okay, this is something we're gonna try here. So you also know that these kind of movements are also possible. We're gonna switch depending on the type of the curve, right? Because we have like linear curves, and then we have like yeah, they call it here polyline curve, but essentially, you know, this is like more circly in this framework. Okay, and we're gonna use yeah, operations with strings, which means operations with text, right? And we're gonna try match text. It works. It's a very stupid component in a way, but it like literally just takes the text to match, and I want to match linear curve. If I do this, for example, with a mistake, it's not gonna match anything, right? So you see, it's false. So it has to be precise. Okay. Let's use shift pattern. So we just have like pattern mask and we just patch it pretty much, right? So this is the mask and this is the list. So now we have line. Let's break that down, right? Lines and curves. Cool. Those are lines and those are curves. Yeah, so you see that it's kind of divides it. Okay, fine. That's, I mean, this is just for optimization. So if they have a little bit of, you know, it looks like it's a line, that's okay for us. Right. So okay, we need to obtain and points. So, we entwine them. You don't need to, and we change it like this. As we did previously, we flip the matrix, right? Simplified. We flip the matrix, and for curves, what we need to do is we need to divide it again. So somewhere here we had our optimization. So let's just copy it. Yeah. We copy it here. Yeah, okay, just to make it simple. Default. We don't need to reverse it, but let's simplify it. Right. Okay, and we merge these guys. Nice. So it looks pretty good, I'd say. Yeah, it looks pretty good. Let's just clean the list, clean tree from everything. So this is the tree, right? Data tree to clean, and this is what we want to clean. We want to clean everything. Did it do something? Yeah, actually, it did do something. Okay, we flatten it. And these are supposed to be our points. Right? To check if what we did is what we want. We do similar shit. Okay. Maybe I'm just gonna unpreview it. Nice. Okay, that's not very clear if it's true. Okay, it's like two different curves. You know what we can try? And I think the previous framework had a similar problem. But we can join them somewhere here. And just flatten it so they join. So now it should be, yeah, I think it looks totally okay. Right? Yeah, okay. That's just perfect. So we group these guys as creating points for fields. With the last block, right, that we have in today's tutorial. And this last block is, yeah, how to actually use it on a real wood plank. Because for now we just had the, you know, like a bounding box, right? Yeah, I decided it would be cool to actually use, this is the model that I got from Valentine, right? It's a model of the real waste wood that we have in the lab, right? So you see how it looks like. And yeah, I thought it's actually pretty useful for us to go through, yeah, what do you need to do to actually use it? Yeah, okay. So first thing is, I suppose, well, let's bring it here, but we need to, yeah, like move it to the table, I would say. Or wait. Okay. We need to obtain the bounding box of this wood plank. Yeah. And that's what we're gonna use in the system, union box, in case it gives the box of every, you know, everything that is inside. And yeah, we'll move it to the table. So for that we will use move component, and the vector we steal from, yeah, this one. Yeah, okay, great. Great. We can also connect the bounding box here. So it already does everything we need, right? Does the procedure in the size that is closer to what we want, the framework, right? Okay, yeah. And it kind of looks fine, but then the problem is that the surface is not flat, right? So we cannot just, yeah, feed like these planes that we have to robot. We need to, yeah, like let's say project it to the surface. And probably the first thing you will think about is, okay, let's preview everything off maybe. Yeah, you would think about this just to deconstruct it, I'd say, deconstruct BREP, obtain, you know, like these surfaces and be good. But that's unfortunately not the way to go with this particular model, because it has way too many faces. And honestly, you know, like each time going through that, when you have different types of planks, no, thank you. We need some kind of, yeah, like more parametric logic to do that. Yeah, what I came up with is to pretty much, yeah, like obtain the cuts somewhere here and just create parametrically, or like reconstruct, you know, only the top surface through the cuts. Because, and like with the cuts, we can also ignore some of the, yeah, like things like those ones. Yeah. So anyway, it all depends on the model in the end of the day, but it's good to learn how to deal with some of the stuff like this one, right? So, okay, we need bounding box. We deconstruct grep here. Actually, I usually just, to be very, safe, do union box. So if there is, the brep is not joined, it's not gonna give me time, a lot of them. It's just gonna give me one that unites everything, and because that's what I want. So we deconstruct brep, and we're just gonna take some of the faces, such as 1 and 3. Yeah. So that's those faces. That's what we need, and we'll obtain the centroids through area component, and we'll create line with the average of them, which is the middle, right? Average of 2 points, the point in between them, let's create a line. So it will be like a line from here to here and from the center to another side. I mean, let's kind of dispatch it, but because we anyway have only 2, we're gonna do it like this. And those are our 2 curves. And we need like a point where we want to create a cut. For that, we evaluate curve. We connect it, we reparameterize it, so we make it from 0 to 1. And let's say the component, I don't know, the place, let's say 0, like somewhere close to the end, right? But somewhere further from like these holes. Same goes with that curve. I mean, you can also copy this parameter, but like now it works fine like this. So let's create a vector. We need the average point, and we need this point. Then we move it. We move. So we need like some kind of a cutting plane, and I suggest what we do is that, we just create a plane. Should have something like this. Yeah. Okay, since we need only 1, because it's 2 here. So let's take only 1. Okay. It wants a point. Plane. We make it a surface. Yeah, you can do that. So it makes a very small surface. And we scale it like a lot. Well, actually, the center can be this, the geometry, and the factor, I don't know, 500. Oh, that's it's not what we want. If we take the volume, draw it. We do this. Okay, great. Better. Anyway, this is the cutting plane. And we need to move it here. And well, same goes with this side. Let's just copy just connect it with this curve. So we have, yeah, like these two cutting planes. Yeah. Okay, cool. Just want to unpreview it. Yeah. And yeah, well, after we created this, we need to pretty much do the intersection, solve the intersection. And for that, we use prep intersection, or yeah, should be here, right? Physical intersection. And what interests us is the intersection of the geometry with the cutting plane. Yeah, same goes here. Okay, so we obtained these two curves. That's good. We can put them in containers. Yeah. And what I want to do is that I want to parametrically understand what is the top surface, right? Without choosing anything, so it can be used whatever piece of wood we feed it. So for that, try something. Okay, well, actually, we don't need it. Let's get the area and let's explode the curve. Yeah, so we obtain this information. We deconstruct the vertices because I want to show you how to, yeah, do it in this way with z coordinates. And my kind of point will be like if this point is higher, like the points is higher than this one, this is top surface. If it's lower, then it's the bottom one. I mean, there are different ways to do similar stuff, but we'll go today through this one. And we'll create expression for that. So if x greater than y, we have true or false. Yeah. And our x is z component, and our y is also z component of the center point. And yeah, we have our pattern pretty much. We can use it to dispatch. Yeah, and dispatch vertices. So now we have the points that are, well, yeah, that belong to the top surface. Yeah, so, and we just deconstruct it. And construct it again at somewhere else, right? We will, so because actually the bounding box is here, I want this point to be in the end, right? I don't want it to be where the cutting plane is located. Cutting plane is only because we have some holes, so we need to be safe when we do when we obtain, right, like these polylines. So let's deconstruct the box. Let's deconstruct prep and deconstruct box, and they give you completely different things. So we have the domain of x, and we just deconstruct domain. And yeah, so this would be, actually, let's put it start domain and end domain y. No, yeah. Oh. Hidden. Yeah. And we use it. I think this one is stars. No. Okay, let's try with this one. Yeah, that's what we want. Okay, that's cool. So we pretty much do the same. We can copy it, right? And do the same thing here with another curve. Only we use not end domain, but the start domain. Okay. So we have these points, and we can just easily create lines out of them. And from lines, we loft the surface in a straight way. Yeah, cool. So to show you what do we have, Control A, and so yeah, we obtain this guy, which is cool. We can name it all of this block. Obtain top surface. Great. So now what we need to do is we pretty much need to project the rails here. We need to project them to this top surface. Why not lines, not curves? Because this is much better, simpler, easier, and we don't mess with the data structure that we already developed. So to do that, it's quite simple. We just need to, yeah, obtain the rails. Yeah. We move them just to be safe up. Unit Z, I don't know, 200. But this is just a precaution, to be honest. And we use project a curve on the B-rep. A curve onto a B-rep, yeah? So that's our curve. The direction will be -1, right? Because it's up, so it needs to be projected down. That's why it's -1. Why it's 1? Because it doesn't matter. Like the number doesn't matter here at all. Yeah, we need this B-rep, which is our top surface. Let's create a box for it. Top surface, real wood blank. And bring it here. Yeah. So, yeah, we did what we had to. We projected it. I think it's those guys, right? So these are the rails, and here we will, decide with length of milling lines, percentage of milling, and the seat. So we want these to be connected with the last part, and this is very simple. We just literally connect it here, right? So we intersect it here with projection. Project curves on a real piece of wood. Okay, that's perfect. Or not, let's see. Yeah, that works just fine, right? I mean, it's a bit slower, obviously, for obvious reasons. But when you create the pattern, I recommend to do it, on an abstract box and just connect it closer to the end when you already decided with the type that you like. And yeah, so let's see. Oh, actually, let's connect the real piece of wood here as well, so we can see this one, right? So we can see not a box, but the real geometry. Okay, how our robot will mill it? Let's check it out. Yeah, maybe abstract table is also something we want. on body. Let's bring it here. Much, I don't know, grayish, right? And just abstract table. We put it here and hidden. We name it table. Yeah, cool. So now we have like the robot here. And yeah, let's check it out. Okay, great. Yeah, cool. So maybe if we put something else, preview all off, only this. Yeah, because we had like red curves from before, right? So we go and we actually see how the lines, are located on the surface that we have, and this geometry has to be very precise in order the whole thing to work properly, right? Yeah. So congrats. You see also how we worked on that in terms of we started from certain things and then we built complexity.
Yeah, exactly.
We built it from more simple to to what we have, and this is like the right way to work, right? You don't start from all this, you kind of start from simpler blocks, you bring it in, you bring things in, and eventually now we have the whole framework, right, from 0 to production pretty much.
Exactly. Okay.